Welcome to qnawire.
All right, so what we have here is a more challenging problem just because there's so many time intervals that are occurring. But if we draw a really careful diagram, then that will help us not lose track of what's going on. So I think it would be most useful to just use a really long number line for this problem because it's one-dimensional. We're only horizontal. We're only the x-axis, so we don't need to draw a whole graph. We don't need to worry about a vertical or y direction. We're just going to draw a number line to represent our x-axis. We can draw a big dot right here to indicate that that's our starting point. That's where the puck is, and our puck starts at a location of x naught is equal to 0, as well as time is equal to 0. So we'll draw that in blue. So we'll say that t naught is equal to 0. And we're going to travel along to 3 different time intervals. So the information that we've realized so far is that it starts off at x equals 0 and t equals 0. I'm just reading ahead. We're going to cross by 3 other times. So those are 2 seconds, 5 seconds, and 7 seconds. I propose naming those by T1, T2, and T3 respectively. So T1 is going to be equal to 2 seconds. And just to save space, I'll not worry about the significant figures on my diagram, but T2 is going to be equal to 5 seconds. And then likewise, T3 is going to be equal to 7 seconds. And then we don't know, well, I kind of drew them evenly spaced here, not to imply that they're all going to be evenly spaced, but these are technically unknown distances as of yet that we have to solve for throughout the problem. So we'll just follow the subscript convention and call them x1, x2, and x3. So this is our schematic of what's going on in the problem, and then the reason why the puck is even moving in the first place is because there may or may not be a force acting on each of these time intervals that I'm drawing in green right here. So what that means is that we have a non-zero force, so that is this 0.25 newtons. So in the first time interval, the force is being applied. And then again, without having to worry about sitting the figures, 0.25 newtons. But in the second time interval, the force is no longer being applied, so that gives you a force of 0. But then in the third interval, the force is again turned on because the player is pushing on again. So we again have a force of 0.25 newtons going on here. So those are the complexities that are going on. We can already see if the force is going to be equal to 0, then Newton's second law, which is F is equal to ma, is going to tell us that the acceleration is equal to 0. But the acceleration is going to be non-zero in the first and the third interval. But anyway, I'm getting a little ahead of myself, so oops. Meant to circle that in a different color. In part A, we will be solving for this position as well as its respective velocity. And then in part B, we're going to be solving for x3, the final position and velocity. So this is our schematic diagram of what is going to go down in this problem. And so let's just go ahead and get started with mathematically with part A. Now that we have our very carefully crafted diagram. So we're actually going to be using kinematics equations, in case you couldn't tell, in order to solve for the positions and velocities. So x1 is going to be equal to the initial position, x naught, added to the initial velocity, v naught. And sorry, these are supposed to be parentheses. the time interval from t1 to t0. I'm going to be super explicit here. Plus 1/2 of this acceleration from t1 through t0 squared is important on the acceleration term. So you can already see here, one other piece of information that was given to us that I forgot to sketch out is that we also know that the puck begins at rest. So in other words, its initial velocity is equal to 0. That really helps us out in this first equation right here, because velocity is equal to 0, so that second term goes to 0. In addition, it starts at the origin, so its initial position is equal to 0. So that will help us out there. So we only need to plug in numbers for the third term. So we have a 1/2 out front, an acceleration that is going to be equal to 0.25, 0 divided by 0.16. Times this time interval 2.00 minus 0 squared, which to three significant figures will give us 3.13 meters. Great, so that's the first half of part A. I think we have enough space down here to squeeze in the velocity. So we can use a simpler kinematics equation, that being v1 is equal to v0, simply added to the product of our acceleration multiplied by the time interval that we're working over. So that's from t0 to t1, no squared, no 1/2. Just like before, we know that the initial velocity is 0, so that first term goes away. So we are just left with that same acceleration, which is force divided by mass. Sorry. There's our acceleration, and then our time interval. Square or anything like that, and then at the end of the day, sorry, it's starting to look like a check mark. V1 is remarkably, it gives you the same answer because of the coincidence that the time interval is 2 seconds. It was squared before, but it canceled out with the 1/2 in front. So this is also numerically 3.13, but it's a velocity, so it has different units. It comes with meters, units of meters per second, and not anything else. Okay. So that wraps up part A. So remember the diagram. Have the diagram written down. We're going to need a new slide, some more space. So we ultimately want to know what the position and velocity are at that third point in time. In order to get there, we have to calculate the position and velocity at x2 first. So luckily there's no acceleration, so the velocity at position 2 is simply going to be the same as position 1, which we said earlier was 3.13 meters per second. However, because we're still traveling at a constant velocity, we will need to apply the kinematics equation again in order to solve for our new position. So final velocity is final position is equal to initial position plus the velocity, that initial velocity along this new time interval, which is from t1 to t2 added to 1/2 the acceleration, just to be super explicit, any potential acceleration that's occurring along this time interval squared. So we know from our careful diagram that we drew earlier that this acceleration is 0, so we don't need to worry about the third term. However, we do have to worry about the first two terms. So we just said in the previous part, we got 3.13 meters to 3 significant figures, but it was actually 3.125. So this is a good instance where when you have intermediates calculations and problems, you should use as many significant figures as you can. Don't round off intermediate answers so that it doesn't affect your final answers. So we're going to be careful and include that. So our new time interval is between 2 seconds and 5 seconds. So that's going to be that, and that will give us an x2 that's equal to exactly 12.5 meters. So we can underline that. That's not a final answer, but it's necessary in order to get to the final answer because we have a new another time interval, this one with a different acceleration, and that's between x2 and x3. So we'll add this to our v2 velocity, and then the time interval from t2 to t3. So we get the 1/2. We have an acceleration again in this interval, and that is still from t2 to t3. This term is squared. Oops, squared. Okay, so none of these terms are equal to 0, so I need to put in something for all three. We just found out what x2 was, and that is 12.5. v2 we said is the same as v1, and to 4 significant figures, that was 3.125. And then our new time interval is from 5 seconds to 7 seconds. That gives us a 7 minus 5. And then add that to 1/2. And then remember that we're calculating our acceleration by dividing the force by the mass. So 0.160 is our acceleration. And then time, same thing, but squared this time, 7 minus 5 squared. Excellent. Plug that all into a calculator, and then to 3 significant figures, you get 21.9 meters. This is x3, which is one of the quantities that they are asking for in part B. Excellent. I didn't even label that we were doing part B. We're doing part B. Here we go. Okay, so we are not quite done yet. The last thing that we need to do, I'll draw us a little box in the corner. We'll work over here now, is to solve for that velocity at time 3. So already know that what v2 is. It's the same as v1 because there's no acceleration. But v3 is going to be equal to v2, plus the acceleration along this time interval, which is from, of course, 2 to 3. Close parentheses. So this should go by pretty quickly. The full unrounded answer for v2 was 3.125. Add that again to our acceleration. And then that same time interval, which I will try to fit. It's a 7.00 minus 5.00. Hopefully it fits, and it fits, yes, okay. Plug that all into a calculator, and then you get a whopping final velocity of 6.25 meters per second. And this is v3. All right, and that wraps up part B. So we are all done.